going to cover the sort of the beginnings of the modern computer era, really starting in the 1930s and going up through a few years after World War II. So first, what constitutes a modern computer? And we won't think about the miniaturization and the particular type of electronics, but I think the key things are that it's digital as opposed to analog, electronic as opposed to mechanical or electromechanical, general purpose, not designed just to do a specific kind of problem, programmable, maybe that's somewhat the same thing as general purpose, but very programmable, a binary, I think that has become the standard, and then having stored programs, okay, that you don't have to be feeding in instructions. Okay, so we're going to go through. There was a period when there were a bunch of efforts that satisfied some of these things, but not all. It was a while till they were all satisfied, and we'll see that. Okay, so the thing I'm starting with is actually doesn't satisfy any of them. But nonetheless, it had an important effect. So Vannevar Bush, and working with Harold Hazen, and Vannevar Bush founded Raytheon. So John Rudy must be smiling somewhere. Created this differential analyzer. It was a totally analog machine to solve differential equations. And it had some electrical parts. It was mostly mechanical. And interestingly, Claude Shannon was hired in 1936 to help run the analyzer. We'll hear some more about Claude Shannon, but I imagine most of you know something about him already. Okay, so although this thing has none of the aspects of a computer as I've defined them, nonetheless, I think it was something that got a bunch of people thinking about, how can we build machines to do particularly calculations. Okay, and someone else who was sort of seminal in this somewhat was Claude Shannon, and he had learned about the work of George Boole when he was an undergraduate at U of Michigan. Then he was at MIT after that, where he did his master's thesis, and actually he was advised by Vannevar Bush. So anyway, he did this thesis on a symbolic analysis of relay and switching circuits, which became very, very important. Although the really earliest people, the host asked you to start your video. What the hell is that?
You have a camera on your computer there, Barry?
I'm going to ignore this. Okay.
Well, he wants to see your face. So if you want to start your video, but
well,
is that up?
I see. Well, what happens if I do that?
Sure.
Let's try that. Oh, if I can. Start video.
What's that?
Then if you tip the camera down a little bit.
Yeah, okay. I'm somewhere out there. Good.
Yes.
Okay. But the very earliest people who did work on computers weren't actually following, his work, but it did become very important later on. And by the way, he also wrote this mathematical theory of communication about errors, redundancy, and communication rate and how they were all related. And he was also the first person to publish using the term bit for binary digit. Okay. Okay.
Now,
Yeah,
okay, try.
maybe this, is this too hard? Should I just skip this?
I heard, as long as you're all, let me power off the speakerphone.
Okay.
Bob, use your emoji to tell us that we're okay.
No, we won't be intentional.
No, but he.
Oh,
He's getting everything.
spot, yes.
We can't hear him.
Good. Now you'll have to put your speaker on.
No sound,
Yeah, we got it.
very faint sound.
In action. In fact, the 1952 whirlwind behind me was the first computer I ever wrote a program.
Is it getting good?
This series, I hope to give you a sense of what it was like to invent computing. See and hear the pioneers and their computers in vintage footage and in later day reminiscences. I will be your guide in time travel, from the dawn of computing in the 30s to its commercialization in the 50s. In the 30s, card calculating, while an advance over pencil, paper, and mechanical calculators, was labor-intensive, slow, and unwieldy. Systems like this were used in the war effort, including the design of the A-bomb at Los Alamos. Scientific problems were laboriously done on desk calculators, took hours and days to do, and were fought with the errors of human input. By 1937, 5 independent researchers were dreaming about computing machines. 4 were driven.
I am sharing.
I'm hearing it well, but.
I know you're here, but you're listening.
Yeah, but we're hearing it bad.
Driven by curiosity and frustration with the error-prone slowness of their own work. They were inner-driven to build a fast scientific calculating machine. The first was Conrad Zuse in Berlin. While a student of civil engineering, he started to work on the design of mechanical aids to stress calculations. By 1936, Zuse had a basic design for a computer whose operations were specified by a sequence of markings on a tape. The same year in England, Alan Turing's paper on computable numbers was published, introducing the concept of a universal computing machine to an academic audience. But none of the others were affected by his paper. At Harvard, physicist Howard Aiken, inspired by the designs of Charles Babbage, was determined to build a machine to solve nonlinear differential equations that he was encountering in his dissertation. At Iowa State University, John Atanasoff was consumed with building a machine to solve simultaneous algebraic equations for the solution of partial differential equations. And finally, at Bell Labs, George Stibitz was experimenting with the use of relays to build a reliable calculator for circuit analysis. Stibitz was the first to get an operation.
Okay.
At the bottom left.
What should I choose? Use. Okay.
You need to mute the audience microphone. Carl, you need to unmute your microphone. Carl, you need to make sure that when you're sharing the video that you've selected the audio improvement button on the lower left of the share screen.
I have.
The audience is still not muted, and thus there's an echo.
I am.
It's coming through his machine.
So,
Okay, are we getting anything now? No.
Yeah, if you close caption using settings, then there's a lot of different ways to get out.
Oh, God.
so now you don't hear me at all, do you?
Everybody?
We do hear you.
You hear him?
Oh,
However,
Does
If
anyone else?
you
The echoes?
if we can use the microphone,
Hearing the echoes, but I'm wondering if Bob and Steve are the echoes. They're not muted.
we are not doing the echoes. We are hearing the echoes.
Are you running the video now?
No, I'm not.
Why don't you run the video and let me hear whether.
Well, I'm not, I don't need to run video now for a while.
Okay, I'm
I
sorry.
just want to get back to showing and talking.
Carl, please turn on your microphone.
well,
Please
it's
turn off the
certainly
audience microphone. Please turn on Carl's microphone, turn off the audience microphone. This is frustrating.
Battery high.
Okay, do you hear me now? Just thumbs up if you do.
You're coming across choppy.
I can see that you're new.
So I need to unmute.
Yeah.
What about now?
We hear, well, you only said the three words, a little more.
Okay, so I am going to. Oh, no.
You need to be. Okay. Can anybody hear me now?
There are two things I can mute. I can mute my Zoom session, I can mute my computer space.
Mute your computer screen. Okay, are we? Can anybody hear us now? Yes.
We
Okay.
hear you, yes.
Someone unmute themselves and talk.
From can I speak a second here? From a recording situation, we want to be able to see the speaker and hear the speaker. And the only way to do that without echo is for Carl to have his video on, Carl to have his microphone on, and Carl's speaker to be the only one working in the room.
That's not the way the system works, though. It has to go through the speakerphone. So Carl's voice cannot come through his own machine.
You can spotlight him with the spotlight feature of Zoom. Spotlight his video without his microphone being on.
Spotlight for everyone. Yes, I got it.
Okay.
Excellent. Now just adjust the angle of the laptop.
Yeah, all right. It's pretty good.
Okay, so I can do that. Can you hear me?
Yes.
Yes, we can hear you and we can see you.
Okay, so I'm not going to.
Share your screen.
Yes. Okay, so at the moment, my Zoom session is muted.
That's correct.
Okay,
I hear you well.
all right,
Good.
good.
This is a
Yeah.
great debugging session for this.
Yes, I know. We should have started out about 2 hours earlier this morning. Yes. Okay,
The voice is
now,
very clear.
That's because it comes from the
I
speaker.
told everybody to come in.
There we go.
okay, good. I showed all of that video that I wanted. Okay.
Let's give them our attention.
Yes. So now, I'm going to talk about the various people who were sort of the pioneers. Of course, Alan Turing was initially was mostly theoretical, writing this, coming up with the idea of this Turing machine, a sort of a universal computing machine. He wasn't actually trying to design a computer. He was trying to prove something mathematically, and he defined a theoretical machine to help him do this proof. But anyway, later on, of course, he was very much involved with the decoding of the German Enigma messages. And then, of course, we also know him for his Turing test, which we're getting pretty close to satisfying. Yes.
Carl,
Yes.
Isn't it the case that people confuse Turing with his breaking of the Enigma, the German code, as opposed to all of his fundamental work that he did long before he started that and long after. And people sometimes think that it's related, and it really isn't.
Right.
Other than he's a smart guy.
He was a very smart guy. Yes. Right.
He did.
Well, eventually he did, but he actually did a bunch of other important things even after the Enigma machine.
Absolutely.
Okay, and just to show you, this is the machine that was built to under his direction and somewhat maybe his hands to solve the Enigma coding. And this was not electronic. It was electromechanical.
One other thing about
Yes.
for people in the Northeast, there's an excellent museum at NSA that you can actually get into and see an awful lot about the Turing's breaking of the Enigma code. And if you happen to go to England, Bletchley Park is an excellent, reestablished place. And you can learn a lot about what Turing did and what they all did. Actually, many more than Turing that were involved in the breaking of the code.
Yes, I actually have visited Bletchley Park, and it was.
Yeah, in both places, though, they basically ignore the work that was done in Poland before 1939 and including 1939 by Marian Rejewski and others who actually did the first breaking of the Enigma and mechanized the breaking of Enigma, but it didn't function electronically. It was only electromechanical. Turing didn't invent that. He learned that from Rejewski and the other people who escaped from Poland to France and eventually ended up in England. Some of them didn't make it, but they were put on the back burner because when a lot of these books were written, Poland was still on the wrong side of the Iron Curtain. But this is visionist history to say that this was done in Bletchley Park. It wasn't. It was the electronic version of it was done in Bletchley Park, but not the mechanical version. That was recreation of what was done in Poland.
Yes, and I'll talk about that soon.
But in Poland, they destroyed everything before the Nazis took the place. So that
yes,
and the guys went through terrible abuse.
Yes.
Excuse me for 1 second.
So
it's my impression, having read the book Breaking the Enigma, they didn't actually do it to succeed. They had to go and grab documentation or tables off boats, like weather boats, or secretly, and then they could break it for 2 or 3 months, and then they couldn't.
Yes.
And then they'd have to repeat, and they had to be careful to not, do it too often. But I don't think they ever really succeeded. And they could break sometimes, but they never gained 100% or close to it.
Well,
yes,
I think we're getting a little bit.
Enigma was a combinatorial problem.
Let's let Carl go on, okay?
I think we're getting a little bit afield. By the way, I
have to
certainly
put
will
it in a
agree
modern
that
context.
there was a very important Polish contribution, and there's some argument about, how much of it was solved before and how much was solved in England. But anyway, another one of the pioneers was George Stibitz, who worked at Bell Labs, and he was a little bit curious, and he brought home from the labs a little bit of junk that they had lying around and built himself a very small relay-based binary calculator in his kitchen in 1937. 1937 was this incredible year when all these things were going on at the same time. So from what I've been able to figure out, his original calculator only did like two binary digit numbers to calculate, but he brought it into work and other people were impressed by it. And then there were various, so then there were various funded operations that did bigger, more complex versions of this. Finally, up to I think the final one was in 1946. But these were all based on relays, so they were electromechanical. They were not electronic, which of course limits the speed at which the thing can operate. And it's believed that he invented the term digital. Okay. Now, also going on at the same time was this man in Nazi Germany, Konrad Zuse. And he, well, there are varying accounts about this and that are not in agreement, but it appears that he built a programmable mechanical computer in his parents' kitchen. He had studied engineering, he studied civil engineering. I think he had a degree in it. And he didn't like the idea of all the calculations that you had to do. And he had this idea of making a machine that would make it easier, would do a bunch of the calculations. So there was no funding for his original model, which is now historically known as the Z1. Later on, and I think he built a Z2 on his own, but I'm a little bit less certain about that. But then he was drafted into the German army, but through some contacts, he had done a little bit of, he had worked for a little while for an aircraft, a German aircraft company before the war. And that, because of his contacts there, he managed to avoid being made cannon fodder and was put to work in the war effort by working again on a German aircraft company. I don't know if it was the same one, to do calculations on airframes. And he built the Z3, which was all relay driven. And he himself was apparently never a member of the Nazi Party. He might think of him like a Werner von Braun. He was curious, he was interested. He didn't pay any attention to the politics going on, which is both good and bad. But he did have some advice and assistance from someone named Helmut Schreier, who was actually the one who suggested to him using relays instead of the purely mechanical thing that he first did. And Helmut Schreier wrote a proposal to the German government for funding of an electronic version, but they turned it down. They didn't fund it. Helmut Schreier was a member of the Nazi Party, and interestingly, after the war, he emigrated to Brazil, which somehow there's a common theme there. Zuse stayed around in Germany. He started, some years later, he started a little company to do computers, and it was, I guess, bought up or absorbed by Siemens. Okay, and he came to the United States at some point and gave talks on the work he had done. So this was his Z3 was completed in the end of 1941. It had 2,600 relays. It was binary, and it did floating point arithmetic, which is an amazing thing. None of the other really early computers did it. It had 64 words of memory, each 22 bits, and the 22 bits were designed to hold, a mantissa and an exponent. Okay, And it could multiply two numbers together, the floating point, in 3 to 5 seconds, which does sound a little bit slow, but faster than people. And it took input from a punch tape. The punch tape was actually not paper tape. It was like old movie stock or something like that with holes punched in it. But it was really an incredible thing. And this was really all his design. And he wasn't, particularly tutored in any of this. So I think he eventually learned about George Boole and Boolean logic, but he didn't know that originally. And he made the key decision to do it in binary.
Did the Germans use that during the war?
I don't think they really quite got around to using it. And then the machine was destroyed in an Allied bombing. Okay. So he had been frustrated by the calculations. Okay, I think I went through this already. Oops, why am I going the wrong way? Okay. Oh, come on.
There we go.
Okay, now we're going to do it. We'll do it right away.
So is that a
Okay.
picture of Schreiner or of?
No, that was a picture of Zusa. Yeah, taken years later. I mean, he was a pretty young man when his early work was done. And this was a later rebuild for a museum of his Z3 computer. So you can see something what it looked like.
That actually work?
Yes, apparently it actually did work. And actually relays are pretty reliable.
Yeah. Okay.
Okay, the next.
You talked about Bell, and that's the whole switching system was built on relays. So
Yes, exactly. That was the Bell switching system worked on that, which is why George Stibitz, there were relays flying around and they got interest in that. Okay, so the other early pioneer, or another key pioneer, was John Adanasoff. He was born in the United States.
He was born in Hamilton, New York.
Oh, all right. Okay. Anyway, he taught at Iowa State University, but I think he had a degree in math from University of Michigan, but I'm not certain about it. I may have that wrong. And once he had a long drive, which apparently was because Iowa was dry and he was driving to some place where he could get alcohol. He thought of the key principles of the computer. Yes. So he actually started on this in 1937, but in 1939, with a graduate student assistant named Clifford Berry, they built an electronic calculator to solve simultaneous linear equations. And the 1942 date was that after they first did this thing on a real shoestring, and then they got a little bit of funding to build a newer model. And the newer model was never quite completed because he was drafted and for the Naval Ordnance Lab given a completely different assignment, and just before they might have completed the machine. And while he was off doing other things, Iowa State University took the whole thing apart.
They were supposed to file patents. They never did.
And they didn't file a patent. Yes. Okay. But by the way, later on, he was declared by a judge the inventor of the electronic digital computer.
All right.
Okay. Yes. So it was later on he named it the ABC, the Adanasoff Ferry computer. Cool.
Very good credit.
Yes, right, exactly. Yes, right. Yeah, graduate assistants sometimes really lose out on these things. So it was probably the first, it was the first electronic calculator, and it did solve sets of simultaneous equations. It wasn't programmable. An operator had to do like each step. So there were a lot of manual parts. But on the other hand, doing some significant number of simultaneous equations can be pretty hard to do manually. And so this did beat out the manual work. There was a punch card reader for input. And they actually made a little device that was sort of a key punch. So it was a homemade key punch. And it had a drum memory, which stored 30, 50-bit numbers. But the drum, it was a big mechanical drum that rotated at one second. And each of the positions had a capacitor, and it had to recharge the capacitors, but it could read whether there was a one or a capacitor had charge or not charge, whatever. So it was really incredibly clever. Oh, also, it was a binary machine, but you punched in the problem, you punched in the parameters of the equations in decimal, and it converted the decimal to binary with another drum that had a series of pins. It was such a Rube Goldberg device, but it was brilliant, absolutely brilliant.
What year was this?
Pardon?
What year did this?
Yes. So they started to work on it in 1937, and they had it working in 1939. So it really was way ahead of everyone else. So and it was electronic. Did I have somewhere the number of tubes? Okay, I guess I didn't have that. But anyway, it did have a large number of vacuum tubes. Okay, I have a video, but I'm going to skip over it because it's too hard. Now, then we get another sort of pioneer, Howard Aiken, and he came from apparently a very difficult background. But then he was working on a physics PhD, and by the way, he wasn't a young graduate student at that point. He had already been out in industry, and I think was actually in the Naval Reserve at that point. He'd been in the Navy. So he needed to do his PhD, he needed to do a lot of calculations for numerical approximation of differential equations. And somewhat by chance, he discovered Harvard University had the papers of Charles Babbage in its collection, somewhere in an attic. And he was inspired by that. And then he managed to get funding with Harvard from IBM. And actually, IBM poured in a lot of money to build this Mark I relay computer. It was part relay, part mechanical. In many ways, it was sort of an updated analog of Charles Babbage's machine. It was a decimal machine, and it had gears that had a position for each decimal. Yeah.
Is this the one they said sounded like knitting needles?
Yes, I think something like that. Exactly when it was running. Okay. It was completed in 1943, and later on, they built newer versions of this, and finally, this Mark IV was all electronic. But I don't know how much he was involved in that at the end. He didn't really think that they needed that. So So here are the details. Somehow there were 750,000 parts in this. I don't know how they can get that number, but here's a description I got. An electric motor turned a metal shaft that ran the length of the machine. When the number was entered there was a paper tape input unit, a clutch coupled one of the Mark I's 3,000 number wheels to the shaft for a specified time span, turning the wheel to one of 10 positions. Okay. When an addition was called for, the appropriate clutch was engaged, the number wheels were rotated, and any carries were relayed to the next number wheel. So this is not that different from what Charles Yes, that's what it was. But nonetheless, it did a lot of useful work. And so here's a picture of the Mark I. It had a fancy front because Thomas Watson wanted it to look really good.
Right.
Yes.
It looks like every other IBM.
Right. Exactly. And notice it says up there, big IBM. Yes. Okay. Now I'm going to go on to the invention of the another electronic computer, but a specialized one. It's Tommy Flowers, who had worked for the General Post Office in England. You have to understand, in a lot of the European countries, the post office was also responsible for the telephone system. And he explored use of electronics for the telephone exchanges. So somehow I've not been able to find how Alan Turing knew him, but Alan Turing proposed him for work at Bletchley Park. And he was the chief designer with a mathematician named Max Newman of two machines to solve this thing called the Lorentz code. So, and by the way, Max Newman was the thesis advisor for Alan Turing. So the Lorentz code was an advance beyond the Enigma machine. So remember, by 1940 or something, they had solved the Enigma machine, but then or late 40, early 41, but then the Germans came up with a more complicated code. So they added at least another wheel and something else to the Enigma machine that made it much harder to break. So I think they sort of figured out how to break the code, but the problem was that they needed to do a huge number of calculations and they just couldn't do them in time. I have a video about this. I'm not going to bother with it. So it took them with something that was they had this thing called the Heath Robinson machine that was electromechanical to do calculations, and it took like 10 days or more to 2 weeks to break the code. However, the Germans changed the code every 24 hours, so it was absolutely useless unless you could do all the calculations, let's say within the first couple of hours. If at midnight they changed it, unless you could do the calculations in the first couple of hours, it was of no use.
I thought the point was that they didn't follow their own rules, and that therefore some of the messages got.
Well, part of the thing that helped, right, was that yes, some of the people did some stupid things.
I think the Germans started a lot of their messages with the time.
Yeah,
So
something like that, right? And then you could look for Heil Hitler in the messages. Yes.
Well, you had to do something that passed the indexing on to the person on the other end, or otherwise it was impossible for the person on the other end break it. Because Enigma, basically, every time you press the key, it rotated the rotors one stop. And then eventually, as they went on to the next decade of them, or next 26th of them, they went on. So you have to initialize it somehow or other. So the Germans were told that they had to put in something that initialized it. And it was finally when that was figured out that that was the key to really unwinding it quickly, because otherwise, the combinatorics went on forever. And when the German Navy added one more rotor, of course, that multiplied everything to 26.
Yes, I think there was something else they added besides another rotor.
Yeah, there was a board the plug board that reflected things, but that actually didn't change the situation. The fundamental problem with Enigma was that you could not encode an A as an A. So once you figured out that there had to be a substitution each time, it just was a question of how long it took you to find the appropriate substitution. And they started off with punched cards, literally with ice picks essentially going through the cards, and then eventually they built the mechanical machine, and then eventually an electronic machine. And it was only when you really had the electronic machine could you get sort of roughly real time kind of decoding.
Yeah. Yes. So
there's a great story about it in the NSA. They have made announcements about these things, nothing recent, but stuff from 50, 60 years ago.
Yeah, thanks. So so there was a lot of opposition to the idea of using vacuum tubes instead of relays, because vacuum tubes were sort of unreliable. And they said, gee, you could never put together, if you had enough vacuum tubes to do all this, it would be breaking constantly. So he managed to convince the powers that be that they could do it. So one of his key contributions was to say, never turn this thing off. Yes.
And
that made a big difference. If you kept it running, it was more reliable. Yes. So anyway, so there was a Mark I that had 1,500 tubes and a Mark II that had 2,400 tubes. I think there was some redundancy in there, but I don't know that much about that. So there's this description that supposedly that when Eisenhower and his staff met on the 5th of June, that he was handed a note summarizing something that the Colossus had just decrypted, confirming that Hitler didn't want to move additional troops to Normandy because he thought that was just a feint. It wasn't the real thing. And that may have been the last part of the decision to go on the 6th of June. And also they had gotten another decoded message earlier that was from Field Marshal Rommel, showed that there were a place that had been chosen as a drop site for U.S. parachute divisions was a base for a German tank division. And so they decided, we're not going to use that place. Okay. And here's a Colossus rebuilt years later.
Where are these? Is this like in Bletchley Park or is this...
Yes, I think this is at Bletchley Park. But I'm trying to remember. What I saw there, I was there about 14 years ago or 15 years ago, so I don't remember that.
Where does the picture come from?
It doesn't say on this picture, but I think it is from Bletchley Park.
Looks like it might be in the lab.
Yes.
The ceiling's not doing too well.
Yes, it does. It does look that way.
You need air conditioning for that, all those tubes.
Right.
Yes.
Did they
Yes.
overheat?
Oh, yes. So actually, someone said that they didn't have air conditioning. He said we had to open the windows. Yes.
It tells me when they had for the original, it was cold in the room, it wasn't cool, it was cold.
Uh, Anyway, and things did break down, but they managed to keep it running enough of the time to do the job. So after the war, this was the machines were destroyed, and the blueprints or whatever were destroyed.
Why?
Well, this is an interesting thing. Suppose it was on order of Churchill, and it may be there was no reason given, but it may be that because they had kept this secret during the war, they certainly didn't share it with the Soviets. It's not clear they shared it with the United States either. And so they may have thought that it was embarrassing, and also that they didn't want like the Soviets to know what they were able to do. But then, unfortunately, the people who worked on it got no credit for many, many years because they were pledged to secrecy. And this is something Alan Turing was pledged to secrecy. And we'll see where that came up as an issue later on. So now we get to the ENIAC, which comes closest to being a true electronic digital computer. And here are the two key people for it, J. Presper Eckert and John Markley. So Eckert was knowledgeable in electronics, and so he did a lot of the electronics design. Markley was the sort of, in some ways, the sort of dreamer, but he was the architect of the thing. And he was a physics instructor at Ursinus College, and not too far from Philadelphia. And he took a wartime course in electronics at the Moore School there. And then he attended an American, I forget what AAS stands for. Yeah, American Association for Science or something like that, that met in December 1940. And he met John Adanasoff there. By the way, he was interested in problems of weather prediction, which did require a lot of calculations and a lot of data. And he was really fascinated by what he heard from Adanasoff, and he visited Adanasoff in Iowa in June 41 and got a tour. He spent several days there. He saw everything about the device. And then he wrote a proposal called The Use of High-Speed Vacuum Tube Devices for Calculating. That was submitted to, this was during the war, it was submitted to the Army, which was doing work at the Moore School. And the proposal was ignored. Now, it could just be, this is military stupidity, but also apparently it was a pretty poorly written thing. And it was proposing to do an electronic version of a calculator. Didn't really have much about, how they were going to do it. S. Eckert met Markley while at this wartime electronics class, and he did wartime research on radar and delay line memories for radar devices. Okay, so he became the chief engineer on ENIAC, and he was only 24 years old when the contract was signed. So he later on, by the way, this was all copied from, I got this slide from something called the Computing Museum at American University. I don't even know if it still exists, which is an old slide. So we called worst design components so that they can operate out of tolerance or specification. But he also insisted that they did prior testing and burn-in of all the tubes, and they would throw away any that, that weren't so good, they were a little bit out of spec. So that was one way that you could get the thing to operate. And they also did a thing of not turning it off. They did modular construction. They had these units with a bunch of tubes that were easily pulled out and replaced. So those were all very good ideas. But there's a third person who's often not heard about in this. Herman, I don't know whether it's Goldstein or Goldstein. I don't know how it's pronounced. I call it Goldstein. Anyway, he had a PhD in math from the University of Chicago, and he was an assistant professor of mathematics before the war. But anyway, he was drafted, and he was assigned to the Ballistic Research Laboratory for the Army at University of Pennsylvania Moore School as a second lieutenant, because he had a course in ballistics and of course mathematics. So but his role there was to oversee the efforts to manually calculate ballistic firing tables. These firing tables were really how you aimed your gun to hit a certain target, and you had to take into account, wind, and each gun, each model of gun was different, and maybe if they had different projectiles that they could load, it would be different for that. And there were guns in aircraft, and that was a whole lot more complicated. So there was a lot of work to calculate ballistic tables, but obviously important in the war effort. And of course, what the manual effort was that they had a room full of women, doing these calculations with pencil and paper and maybe little mechanical calculators.
The astronomers, the women astronomers at Harvard, they were called calculators.
Yes, right. Yes. Or sometimes computers.
Yeah.
Yes, they were called computers.
Yeah.
So when he was there, he heard about Morkley's interest in computation, and he was curious, and he followed up about it. And he realized that, gee, here was something that could make a big difference. And he managed to arrange, I think, first of all, even the original proposal was sort of lost by then, but they had some notes that a secretary had made that they put together. But I think he also sort of coached on improving the proposal and got a meeting together with the right contacts in the Army. And then they got funding. Of course, this was more than a year later. So that was an unfortunate time that was lost. The result was they didn't finish it in time for World War II. But anyway, so right, but not to worry, we had more wars since then. Yes. So anyway, let's see, most of this is the same, but it was used to do computations for the H-bomb design, because it was, in 46, I think, because it was the most powerful thing they had. And
It's not until about 1950.
well, maybe it wasn't.
Before that.
They were designing it well before that.
Well, they were doing stuff, but
Even before
they
the
didn't
end
have
of
an
the Second
idea
World
yet.
War. Oh, yeah, they did.
Oh, no.
you had to wait for Dollar and.
Ulam.
They were doing the 40s in the
Yeah.
early and mid 40s.
Okay. So anyway, this was a thing that had 18,000 vacuum tubes, 70,000 resistors, 10,000 capacitors, and weighed 30 tons. And this was, I think, another thing. This was also a thing where they had to convince people that you really could do it, that you could have this number of vacuum tubes keep running. So I'm sure they built in a lot of redundancy. That's the only way you could do it. Now, why did it need so many vacuum tubes? One bad decision that they made was to make it a decimal machine, because they were emulating calculators. And it took a lot of tubes to do that.
I wonder how many how long it would work without one of those tubes going south.
Well, yeah, I think like, you know, I think at one point it ran for 2 days without a tube going.
Yeah, that's why necessity was another invention. That's why they did all the reliability engineering and the modular construction to keep the uptime.
Right, exactly. So it was a decimal machine. It was programmable, but with great difficulty because you needed patch cables and switches to make logic, and there was no ability to make logic decisions based on numeric results. Now, you have to understand that this was the war. They probably knew that there was more that they could do better, but they were trying to do it fast enough. And for ballistic calculations, they weren't going to be doing a whole lot of different kinds of problems. So the programmability was considered to be not that important.
So this was all used to put it in the books that they'd send out to the field on the ballistics?
I think so, yes,
Yeah.
right.
Okay.
Yes,
So
produce
it's-
tables
in
print
books.
that could be printed and
Yeah.
sent out to the field that people can
Put
consult.
it on their phone.
Yes.
Yeah.
Yes, these were the tables, for the artillery. My great aunt worked on these as a manual programmer.
Oh, by the way, one other interesting historical thing about ballistic, calculations was Harry Truman got his real start that really helped him along in later years by being in World War I. He was good at math. And somehow he got to take like a short course in the Army in doing ballistic calculations. And eventually he became the head of the Battery D, which fought in France near the end of World War I. Yeah. Yes, quite interesting. By the way, he was in modern times, one of the least educated, but the most knowledgeable of our presidents. He was very, very widely read. He was a big reader, and as I said, he was a sharp guy, and he was good at math, among other things. So anyway, back to this thing. So this machine had 20 10-digit accumulators, and there's something like each accumulator. Somehow they use 30 vacuum tubes per digit. So the memory technology was vacuum tube flip-flops. The flip-flop circuit had been invented many years before. And by the way, I presume all the relay things also must have been flip-flops. Something that could stay in a stable state, but switch back and forth. It had a 200 microsecond cycle time, which is really pretty good. And an IBM punch card reader, and a card puncher, and a card printer, the input-output devices. So this reduced a 12-hour manual ballistic calculation to 30 seconds. Yes, of course, they said they got it done by the end of the war. But I'm sure there still were ballistic tables that they needed. Later on, there were new guns all the time. Okay, so this was also a slide that I copied from this American University Computing Museum about the audacity of the project. It's saying that you sort of like try to advance cautiously usually in engineering. So the largest electronic device at the time, at least that they knew about, was a classified radar that contained 300 to 400 vacuum tubes. Now, I guess at the same time, they were building the Colossus in England with many more vacuum tubes than that. I think it was 1,500 was the first one, but I don't think they knew about that. So they thought that this was the most that had been ever done. And the design was going to contain 18,000 vacuum tubes. So it was criticized by many people on that this thing could never work.
So it's 60 times bigger than the other devices.
Right,
radar devices.
right. So anyway, here's some of the ENIAC. And okay. Yes, I'll show you, there's some other pictures there. So the big controversy was about this, became later on, was about this Markley and Adanasoff talk and Markley's going there. And in 47, Eckert and Markley applied for patents on the ENIAC. And it eventually, they did not end up getting the patent because of prior art, John Adanasoff. Yes, there was another reason about publication, pre-publication, which I'll go into later. Okay. So anyway, this is all about programming ENIAC was a one-way ticket to the madhouse. You did not sit down with a computer terminal type of instructions. You set thousands of switches and plugged in hundreds of cables by hand, one at a time. In general, it took about 2 days to set up ENIAC to carry out a program. Now, once you did that, then you fed in all sorts of different numbers as variables. So, it maybe after those 2 days, you ran it for a long time before you needed to reset it. And that's because of this, they didn't need to do that often. Now,
Where's the ENIAC built, or where's it located?
well, it was built at University of Pennsylvania, but when it was completed, it was moved to the Aberdeen Proving Grounds in Maryland. And that's where these calculations were done later, like the H-bomb. But anyway, I want to show you. So here are 3 people who are programming the ENIAC. Do you notice something about them? They're all women. Everyone who worked on the programming of the ENIAC was a woman. Men did the hardware, women did the software. And it wasn't like they had a manual to work from. They had to figure out from circuit diagrams what they needed to do. Now, there's some, Herman Goldstein had some involvement in that and probably did a bunch of advice, but these were pretty sharp women who figured out most of it themselves. So here are the programmers of the ENIAC who didn't get any credit until many years later. By the way, late in the project, Adele Goldstein, who I assume was Goldstein's wife, and Clara von Neumann were joined the team. And I assume that they were pretty sharp. But there was this ad in 1945 that the Moore School run about asking for women with degrees in mathematics.
Yeah, that would be illegal now.
Yes, I guess it would be.
That's right.
But right. But actually, I mean, one of the reasons why you needed women were all the men were off at war. Yes, exactly. So anyway, then I just show another woman pioneer, was Grace Murray Hopper. Murray was her maiden name, Hopper was her married name. Well, apparently the marriage didn't last all that long, but she kept the name. So she had a PhD in math from Yale. And I have to say proudly of my alma mater, Yale, that a few years ago, they renamed one of their 14 residential colleges for Grace Murray Hopper. The reason they renamed it was that it was Calhoun College, named after John C. Calhoun. the great slavery now, slavery forever was what John. Yeah. So I think that was a wise decision.
There were stained glass windows in the dining room that had pictures of workers in the field. Some kitchen worker took a fire poker and broke it.
Yeah, that's good.
He just let go, but then refired.
What year was that?
Oh, that same period, 5-7 years ago.
Yeah,
Of course, they never sent the money back.
right, okay. But anyway, so she got her due there. She also got the Presidential Medal of Honor, actually conferred by Ronald Reagan. So she joined the Naval Reserve in 1943. She wanted to get into the Navy, and they were taking in some women, and somehow she talked her way in, even though she didn't meet the physical requirements. She was really very small and thin. But anyway, so we tried to figure out what to do with her, assigned her they were funding along with IBM, the computation project at Harvard to Howard Aiken. So she was assigned to that. And by all accounts, Howard Aiken, who is not the most open-minded sort of guy, was horrified when he was assigned a woman to be his chief assistant. But he found out pretty shortly that she was really quite good. So
interesting story. I went to a lecture she gave, and she was handing out pieces of wire about a meter long. And she said, "This is how you know how long a nanosecond is." It was either a nanosecond or a picosecond or something,
Yeah.
but she was talking about how far light travels. And
yes, I think it was a nanosecond. Yes,
It's a nanosecond, and it's only a foot long, 30 centimeters.
Okay.
yes, okay. A foot,
We also
not a meter,
called it
probably.
bug, as it they say.
So anyway, she co-authored 3 papers on the Mark I, and then later on, when Eckert and Markley started their computer company, this is sort of jumping ahead a little bit. I'll get to that. She joined that, and so other accomplishments aside from being, the programmer at the on the Mark I, were that she created the world's first compiler, as far as is known, for what was the UNIVAC, and she started the world's first software division for UNIVAC, and the Flowmatic programming language, which was a forerunner of COBOL. And then later on, she was brought back into naval duty to manage the effort to develop COBOL, because they were trying to get something that would work across all government uses. Okay, so I did mention one other thing, that one of the things that she did with the Mark I computer was that she was given a problem to program that required a lot of calculations, and it was something about implosions. But I think she didn't know what it was actually for. It was top secret. They wouldn't tell her, but it was what they used for the A-bomb computations.
No. H-bomb.
A-bomb.
Yeah,
The
the A-bomb.
A-bomb.
A-bomb is done in 1945.
Yes,
And the
yes,
implosion calculators are 44. Is that fits?
yes, that
The
fits.
implosion was for the plutonium bomb.
Yes, yes. So remember, she was assigned in 43 to work up with Howard Aiken on the Mark I. Okay. So anyway, now we'll get to another pioneer, John von Neumann. And probably a lot of you have heard of the von Neumann computer architecture. Yes. So, he was an immigrant to the US from Hungary. He was a mathematician. He was a physicist, did work on quantum mechanics. He was an applied mathematician. He worked in many different areas. I mean, this guy was an incredible genius. So he got an appointment in 1933 to the Institute for Advanced Studies at Princeton. And then later on, he worked on the Manhattan Project. And he joined the ENIAC project in late 1944. And this was another incredible chance thing. Again, Herman Goldstein, back in the picture, ran into him at a railroad station. And Goldstein recognized him from pictures he had seen and went up and started a conversation with him and told von Neumann about the ENIAC project. And von Neumann, who was, I think, thinking about the Manhattan Project and the like, also realized that this could be another great thing. And so he became involved in the ENIAC project. Of course, the ENIAC had already been sort of designed, it was being built at that time. But then there was a design to follow the ENIAC, which was going to be called the EDVAC, the Electronic Discrete Variable Automatic Computer. So this one was to be binary. And by the way, that was one of von Neumann's contributions. He said, don't do decimals, use binary. So it was designed as a binary stored program computer. And the project was started even a little bit before the ENIAC completion. So at least the design work was started. But it was eventually built, but a lot of key people were lost for various reasons, one of which included Eckert and Markley. But so it wasn't so much the actual machine, but von Neumann wrote up a design document for the machine, which became really seminal for work on computers. So this thing eventually had 6,000 vacuum tubes and mercury delay line memory. Now, why did it have only a third as many vacuum tubes as the previous one, the ENIAC? Because it was binary instead of decimal. And it was delivered to the Army Ballistics Research Lab in 1949, but it didn't work reliably for a while. I think they had problems with the mercury delay line memory, so it didn't work reliably before 1951. So think of it this way: you had this one tube of mercury, and I think you had sound pulses going through, and they traveled slowly in the mercury. And so you sent it from one end to the other, and then you sort of regenerated it and sent it back. And
that's the wave.
The waves, yes. It does seem like incredible Rube Goldberg thing, but some of the early computers really depended on that.
So what's stored is the wave going back and forth?
I believe, yes, I believe so. The wave.
Of the light line.
Yes. Right.
Think of the mercury delay line as a shift register memory for those of you who are electronically inclined.
Oh, thank you. Did people catch that?
No.
Oh, that was, think of it as a shift register memory. Yeah.
And
Okay.
it worked particularly well for something like ENIAC or its successor because they didn't do the calculations in parallel. They did them in series.
Yeah.
And so a shift register was perfect. Whereas if you had 16 bits or something being calculated in parallel, that would have been not very useful.
Yes. So now the controversy about stored program. So Eckert and Markley had thought about having stored programs even while they were working on the ENIAC and before von Neumann joined the effort. So it wasn't his idea to do that. But they hadn't gotten around to outlining a design for a stored program computer when von Neumann appeared. So von Neumann came up with a proposed set of instruction codes for the successor computer, the EDVAC, and a logical design for it, and the recommendation to use binary arithmetic. So he wrote a report that was called a first draft. And I'm going to, and I don't know if any of you could see this, it's a little bit of an eye chart, but first draft of a report on the EDVAC by John von Neumann. It was dated June 30th, 1945. Again, this was slightly, I think this was just around the time when the ENIAC was coming close to completion. Oh, okay. So anyway, Herman Goldstein, who was sort of managing the effort, circulated this first draft widely. Von Neumann had intended it to be sort of an internal document. Goldstein thought, gee, this is a great document, and he circulated to a lot of people. And so Eckert and Markley weren't thought of for a while as the originators of the idea of storing programs. But certainly there was a lot about the computer design that was von Neumann's.
Babbage now?
I think Babbage had the idea of stored programs too. You're right about that. Okay, and this was the von Neumann architecture. I won't go into that in detail. So the next important thing in this saga was the Moore School lectures. So the Pentagon wanted to, okay, now we've got something really good. We want to get more minds working on these things, and they're probably thinking mostly of war applications. So they arranged and funded an 8-week course given at the Moore School in the summer of 1946. And the idea was to disseminate the ideas that were developed for the EDVAC. And the various lectures, so they had a series of lectures that were given over this 8 weeks by Eckert, Markley, Goldstein, von Neumann, and others. So this would be a fantastic thing to go to. Yes. Yes, exactly.
Speaking of time, we got about 10 minutes left.
Yes,
right?
okay. So there were 28 students invited to this. You had to be invited by the Pentagon. I know invited students. Somehow there were a few others who managed to get last-minute invitations. So many from the U.S. government and military, some from academia, is all the U.S., and some from the UK, which of course was a close ally, and they were willing to share stuff with the UK. Okay, so now I'm going to go on to something that then after the war, Alan Turing designed a machine called the ACE, or automatic computing engine, and it was supposed to have an operating speed of 1 million pulses a second, 10 times faster than ENIAC. And so this was on the National Physics Laboratory. They were very hesitant about this. They said, gee, seems like too hard a thing to do. They didn't know that it had been done during the war, and the Colossus project, which was all top secret. Turing knew about it, but he couldn't tell them anything about it.
In the same country.
The same country. It was not allowed to be shared with anyone. You couldn't take the papers to Mar-a-Lago, for example. Yes. Yes. Right. Yes. So anyway, he not only did a lot of the design of the machine, he drew up a roster of programs for the ACE, composed in a partially numeric, partially alphabetic code, which some people say were the first bona fide programs. But anyway, so the physics lab decided, oh, this is too ambitious, and they wanted something very scaled down that was called the pilot ACE, which was constructed completed in May 1950. But, and that could have been the first completely electronic stored program machine, everything. Turing got disgusted with them because they just were so slow and hesitant. So he left and he went to Manchester University, where another computer project was underway. And this is the Manchester Baby Computer, or the SSEM. I don't know what that stands for. So it was developed by a team there, led by Tom Kilburn, Frederick Williams, and Jeff Tutel. So Williams invented the cathode ray tube memory. So the idea was that on a cathode ray tube, you would flash a pattern of, you have a dot for each position on the tube could be a 1 or a 0, but somehow was able to sort of read it back. I'm not quite sure how that worked.
Well, the phosphorus had a long persistence, and it was also a random access memory. As opposed to
Right, it was random access, yes. So that was far better. And they eventually got to 2,000, 2K bits per cathode ray tube. And so the whole idea of this computer was to be a proof of concept for the cathode ray memory, which would be by far the best memory that they had for any computer at the time. So they got this thing working in June of 1948, and this was the world's first fully electronic digital stored program computer. And by the way, so Alan Turing came there really after they had designed the thing, but he wrote one of the first programs for it. Okay, and later on, it was followed by the Manchester Mark I. And here's a picture of what they call the Manchester Baby. The Baby, because it was designed to be a smaller version of what they were going to build later on, the proof of concept. Okay, yes, there it is. Okay, so this was the first. Okay, I'm going to skip over this. Meanwhile, back in the US, well, not the US, then another British thing was the EDSAC that was designed at Cambridge University. And that was inspired by, they read John von Neumann's report on the EDVAC. And so they followed that in designing it. And it was in use from 1949 to 1958. To 1958, it had a primitive assembler in 1949, possibly the world's first. And it was supported by a company, J. Lyons and Company, which is like a grocer. And it gave rise to what became the Leo, the world's first computer to put into commercial use. And there's the EDSAC. And I don't know if this was the actual original or another rebuild. Okay. Meanwhile, Eckert and Markley left UPenn to start a company. UPenn, they wanted to patent their computer. UPenn wouldn't allow them to patent it. So that they left UPenn, and that was the thing that they left the EDVAC project, and they started Eckert Markley Corp. And they were, however, bad business people. They made the first customer they could find was the US Census Bureau. They signed a fixed price contract before they had done a lot of the design and development of the machine, and it ended up costing far more. They couldn't get the Census Bureau to let them out of the contract, to let them renegotiate the price. So they ran out of money, and they were purchased by Remington Rand, which later became Sperry Rand, and that the work then became the UNIVAC computers. The first one was delivered to the Census Bureau, 1951. This Remington Sperry Rand lost money on it, but they were hoping to make it back with successor ones, and they had some money. Okay, and they were the ones actually who were funded a patent fight over this, but it was lost because Adonassos' work, and also apparently because of the publication, the John von Neumann publication. Okay, so the UNIVAC 1 had 5,000 vacuum tubes. It stored its programs on magnetic tape. And it had 1,012 character words of mercury delay line memory. It's mostly a decimal machine because that's what Eckert and Barclay really liked. And there were a total of 46 systems delivered.
Is that higher than anybody else in terms of systems?
I think
at that point?
Yes, although it was probably overtaken by the end of the period. But anyway, here's the UNIVAC 1. There's the console,
Using tape drives?
operator's console. Yes, they had
So
magnetic
that's-
tape drives.
that's another innovation.
Yes, that was an innovation. Yes.
And
And then here's this thing at the an interview with Walter Cronkite. Sir, tell me, Walter, what are you going to do to report this very historic election? And Cronkite said, well, we've got this new thing here. We're using electronic brain, which a division of Remington Rand has in Philadelphia. And he says it's going to predict the outcome of the election hour by hour based on returns at the same time periods on the election nights in 1944 and 48. Right, that makes a lot of sense. And it says, actually, we're not depending too much on this machine. It may just be a sideshow. And then again, it may turn out to be of great value to some people. Yes, so it turned out it correctly predicted the result of the election early in the evening. CBS didn't want to report it yet because they didn't have confidence in it. Somewhat later in the evening, they did report that. And of course, it predicted Eisenhower's, yes, it predicted Eisenhower was going to win. Here's another early computer, which we didn't know anything about until the fall of the Soviet Union and get access to the records. They had developed a computer at the Kiev Institute of Electrotechnology. It was started in 1948, became operational in 1950. It had 6,000 tubes, 20-bit word, 31 words for data.
do we know how much they were getting from the West? The way of information?
I think we don't know. I would guess that they had a fair amount. They were usually pretty, yes, they were pretty good at spying. It had a 5 kilohertz cycle time, which I think is pretty similar to the ENIAC.
The first A-bomb is a beautiful copy of.
Yeah, yes, yes, yes,
The H-bomb is.
yes. It was a binary machine of fixed point. Okay, and of course, yeah.
All the airplanes were copied.
I'm going to skip over some other stuff because I think, are we out of time or almost out of time? Yeah, just at the Institute for Advanced Study, they started this computer project for called the IAS computer, Institute for Advanced Study, that was on the direction of von Neumann and the various other people. Herman Goldstein was there, and it was a limited operation in summer 51, full operation 52. So, and it used the Williams tubes, the cathode ray tube memory, had 1,700 vacuum tubes and used 40-bit words. So the machine itself was not that important, but the plans for it were widely distributed, and the computers were done. They were all one-offs, but that was sort of based on the IAS design. There's the Johnny-ac and all kinds of Maniac and all kinds of other names like that. There's von Neumann next to the IAS machine. And there was some short size. Howard Aiken told the National Bureau of Standards, which was backing Eckert Markler's commercial efforts, there'll never be enough work for more than 1 or 2 of these computers. You tell us, let's go back and change the program entirely with this foolishness with Eckert and Markler. Okay.
And Watson who
Yes.
said that.
So here, now I'm going to show, yes, here there was a machine called the SEAC, SEAC, okay, that was done at the National Bureau of Standards around that time. So I assume that some amount of, there was some amount of input from the, the von Neumann paper and maybe even from the IS machine, although they completed this soon, the IS machine. And this person in the picture is Samuel Alexander. And is Mike on this?
Yeah.
Okay,
He was here.
he was on it.
Yes. Yeah,
Yeah, I'm here.
Yes, yes, okay. Oh, OSSEM, small scale experimental machine, okay. That's Mike's father.
Oh, really?
Yes, I just found that out from Mike the other day.
This person?
Yeah, yes, because I saw this name and I asked Mike, I said, is he any relation to you? I said, that was my father.
Wow.
Yes. So anyway, so he designed and built this machine, and this
Can I interject something here? We'll
Please.
go with your history. A couple of people working for my dad really did the design. Dad was kind of, well, more than a project manager, but he was that. One guy, Ralph Slutz, had worked at the Institute for Advanced Study, and he got into arguments with von Neumann about how the computer architecture should be built. And he finally left, and Dad hired him. And he was, in terms of the electronics, it was Ralph Slutz. That's spelled S-L-U-T-Z. Ralph was probably the electronic designer. The logical designer was a guy named Alan Liner, L-E-I-N-E-R. But the Institute for Advanced Study machine was connected to the SEAC in that sense.
Yes, and I think I've seen a list of what they call IAS machines, machines at least inspired by the IAS, not necessarily, they weren't all identical. Probably each one was a little bit different. There was one of each kind, and this was called one of the IAS machines. And okay, I have some eye chart of early machines that shows the MESM of the USSR. Anyway, and I'm sorry, Mike, this didn't list the SEAC, but I think it was also may have been the world's first functioning. So it was a functioning stored program computer. I forget now what it was probably first in.
SEAC was commissioned, I think, in either May or June 1950. And I remember being taken to a party there. I was all of 9 years old, where there was a great big banner, was at night, and it says, "It works."
Yes,
Mission accomplished.
right, mission accomplished. Yes. Yes. Okay, and that's
Was
my
all I
story.
understood.
I'm sticking with it.